Right, welcome back. So this is the work one of my student kind of thinking about how to simulate attack, large scale attacks. And so there are a number of ways. One, if you're working in this in this sector, smart grid or power grid, whatever you call it, either you have to access to the real infrastructure so that you can run attack, simulate and understand in a more realistic real-time environment, which is kind of impossible to get because these are real-time systems. If any company give you that access, that means, and at any point of time anything goes wrong, then they lose their reputation. They might, those experiments might damage their component and so on and so forth. That might also have impact on their safety system. So what we do, second, you can create a test bed. More specifically for research, you can create a small version of it where you can deploy some devices, create a small setup, and you run some experiments on to this. Now one of the, which is good because you can have realistic devices that are being used in industry, right? So I remember when I was a postdoc like 10 years back, we were having a project of US Department of Energy, and we wanted to test a similar thing. So, and there were two power companies involved in the project. So one of the constraints was how you test it. You were talking about an attack that this will impact XYZ, but how are you going to model it? How are you going to test it? So what we did at that point in time, we bought new devices, and then we created a setup, and we utilized one of their isolated locations. Yeah, so they gave us kind of a little part of it, saying you can connect your own device. Yeah, we will give you connectivity, but your attack will not move there. Your attack should be within the devices that you have. So you run the command within what you have and then test it. Test bed, most of the university now have some sort of test beds, which are representing a kind of smaller system of the realistic system. But one of the key things for this kind of test bed is they are not scalable. Yeah? If your research is around device level security, test beds are excellent. Yeah? You're looking at one device and security of it or whatever. For example, if you're looking into mobile security, handset, you can have a variety of handset and you can possibly do this. Easy. What we are talking about is large scale system. They're too complex. You cannot have test bed of those systems. Even if you are able to, if you got a couple of devices, you can run and set up and mount an attack and understand something. You are still talking about a very small system. However, the actual system is much bigger. So maybe the simulation, the results you are seeing on local system, they will not reflect on the realistic large scale systems. So the choice that we have is this simulation environment. Either you create simulation tools or you use some of those tools which are capable of simulating large scale systems, right? So generally in those kind of situations, we go for simulations, software simulations, where you can customize them and they support some kind of scalability. So in this process, what we did, we created a simulation environment. So we developed a prototype of co-simulation that emulates typical smart grid system, mount cyber attack scenarios to evaluate develop tools from the attack perspective, and identify indicator of compromise. So you're creating an attack, mounting it over the environment, physical system, understand what are the indicators that says these behaviors have changed. There are different patterns to that. You extract those indicators and try and understand what is happening to the system. And you do some study out of it. So the question what we answering is, how can we achieve continuously monitoring and identifying iOS in industrial control system? As we said, indicators vary as per the context, as per the application that we are talking about, yeah, for OT system. So the indicator that we have talked about, they all are, some of them may be applicable, some of them may not be applicable, and they can vary depending on the type of attack we are talking about. So it's quite difficult to accurately study and evaluate attack behavior in this process. So what we do is we look at, okay, what kind of simulation tools are available, what their capabilities are, what kind of attack we can target, what kind of results we can evaluate, yeah, and understand. There are a couple of challenges in terms of working on ICS system. One is complexity and interdependence. So what generally is available in the market, for power system, there's a power system simulations. For example, vehicular network, vehicular system, there's a car simulations, and so on and so forth. Yeah, maybe healthcare, there's a healthcare-based simulations. They are not cybersecurity. They are not supporting cybersecurity. Maybe the software that we have having cybersecurity, they are not doing anything with healthcare or power system. So these are isolated systems. You can test cybersecurity, but more in IT environment. You can do power system, but you can't do cybersecurity in that. Yeah, so there's no system, there's no integrated system that can help you to say you can mount an attack and understand things. Second, if you look at more kind of older software, they are not scalable enough. And since they are hard-coded or open source, they're not easy to extend it in terms of functionality. They're so complex you don't understand, so you don't really get a sense how to extend them. Some of these software don't have capability in terms of decision making, how you can, what data and what extent of data you get, and how this data help you to make certain decisions. And there are matrices, and data collection is very limited. So with those kind of context in mind, some simulation just directly simulate, but without giving you any indications that you can derive out of it. Because if you are able to collect data, then you can process and see, in normal scenario, my data should look like this. And in the attack scenario, if it is behaving, you just compare those from the baseline. If you have a variety of data, it will help you to do several things. But many of the simulation do not give you that kind of capability. So what we did is we tried to develop our own simulation environment. So we designed, based on typical infrastructure smart grid system, primary data flow, Modbus. Since we are in UK, so UK, European Union, we use Modbus, not DNP3. All right, so we use DNP3. So in this case, we use Modbus. And this is based on master-slave communication model. What is master-slave model? Have you heard master-slave? What is that? Following, okay. All right, so there's a master that will always give instruction, and slave doesn't do anything until it receives instruction from master, and it does it. Yeah. So in this case, we created multiple substation in a simulation environment. We go control center, number of devices there, and we mirror IDS on that. And this is how it looks like. So we got three components of the simulation environment. One is called cyber communication module. The other is called control center module. The third one is called power system management module. In order to run the whole cycle, we need power system. We need communication network that connects IT to OT, and then you need some sort of IT system. Yeah, and then control center that can send commands and to change data and open circuit breakers and so on. So the number of open source software that we have integrated to this. One is called core network that we use for communication module. There's another called SCADA BR we use to represent SCADA system. Then there's Open PLC we use for representing PLC functionality to this. And then we use Power Word Simulator. So this is how it looks like. Yeah, so you got loads and buses and generator and blah, blah, blah. So this is the Power Word Simulator. So our goal is to, sitting at control center, we want to fetch data So you sense data from the field device, right? Through communication passed to this SCADA system through PLC. You're processing, you're running some algorithm, understanding how the system states look like. If you think there's some lines are overloaded and things like that, that means you need to make certain action. So you need to send certain commands, maybe to reduce something, increase something, detach generator, increase the capacity, reduce it, depending on what is required. Yeah. So you pass that behavior in this power word simulator, and you did that take action. So that's how you understand how an attack can impact your physical system. If it does, is it possible? How easy and difficult for you to recover it? If you take certain actions, send few commands, will it help you to fix things? Sometimes if lines are too overloaded, your components are damaged, it's hard to recover them. Yeah? And in most of the time, those situations where there's a coordinated attack, you're not just opening circuit breaker, but also targeting, for example, generators. If generator don't work, right, there's a problem. So we created that kind of environment in virtual machine, VMware, using VMware. So I just talked about this. So this is the communication module. We use core called Common Open Research Emulator. This was developed by US Naval Research Laboratory. It provides a platform to run different applications, such as IP tables for firewall. What is IP tables? Help manage what are the IPs, inbound and outbound, and so on. Snort, have you heard Snort for IDS? It's a tool or software that you can use to, it's kind of a Wireshark. Yeah, what is Wireshark? By the way, possibly we'll do some exercise with Wireshark. So if you don't have Wireshark on your laptop, please make sure you install it. It's open source software. You can freely install it. Yeah. So Snort is kind of similar application where you can detect the traffic or fabricate packet and then inject it into the in the traffic. So you can do this by Snort. Because those are the things, how are you going to understand whether your attack is working or not? How are you going to validate this thing? So we have these tools, Snort or Wireshark. So what I can do is, if I'm modeling an attack, sending a malicious packet from this device to another device using this Wi-Fi, I can have a monitoring system. So I can look at all the packets as well. Because in order to validate, you need to identify this is the packet. So you create a fabricated packet and send it. You have a monitoring system, for example, Wireshark. Yeah. So Wireshark has capability to capture the network, if you have a permission, of course. Otherwise, it's an ethical thing. So what I can do, for example, I can have a Wireshark. I can start capturing traffic, all the devices which are connected to this Wi-Fi. And I can get to know what you guys are doing at this point. If you're using internet, I can get a sense. I can capture all the data and can analyze in this hour, in this class, what people have done. Yeah? And then when we wanted to inject an attack, we also wanted to test how impactful is it possible for people to figure it out that this is a fabricated packet? When you capture that packet, you analyze this thing, are you able to distinguish this seems to be suspicious packet? As an attacker, your aim is to design a packet in such a way it can bypass the system. So we do this kind of activity, but you also need Snort or Wireshark or whatever to monitor things. Then you got SSH, Secure Cell, that allow you to connect remote devices and so on. Again, it's good for a scalable system. What is VLAN? Core module VLAN. So through VLAN, we connect this module to control center module. What is VLAN? Virtual LAN. What does it mean? Network. What is the need of VLAN? So LAN is local area network. What is virtual LAN? Why we need it? So So when you are talking about local area network, we are talking about physically connecting devices, creating a LAN, connecting a local network, yeah, all the devices that we have PCs. I might have multiple LANs in this institute, but I want to use one of the PC in this lab, maybe another PC from another lab, third PC from another lab. In order to do so, you have to put them all together. That might be possible physically, might not be possible if they are too far or whatever. But since they are part of the network, I can create a VLAN, virtual LAN, and I can decide which devices or PC should be part of this LAN. So I can pick devices from different LANs, put them together. That is the virtual LAN. Yeah. Then we talk about control center module, which is having two parts that works on Modbus master and slave model, SCADA. SCADA BR helps you representing your SCADA server, SCADA system, and then OpenPLC will help you to design your programmable logic controller, where you can put some logic, what to control, and what are the instructions you want to send. So it's an open source human machine interface editor called SCADA BR. So there are people sitting at substations, they are having access to HMI interface. So if they find that something is wrong, some label is going up or down, whatever, so they can send command locally. Yeah? To reduce something, to detach, attach, whatever, at local level. But then they have only understanding at that particular substation. They don't know the big picture. People sitting at control center having a big picture because they have multiple substations, and they're fetching all the data and processing it. But the person who is working on substation only have understanding at local level. They don't know what's happening at this other substation or other locations. So we send operational data to the security module. And so what is this? It's interconnect, using VLAN interconnect. It can pass values from communication network, sense data, pass this, all the power measurements, and then you can test those measurements on the power word system, sorry, this one. So as I said, power word simulator, it's a commercialized simulator, but they also have their free version for educational purpose. If you are doing research or just wanted to use it, so they have a smaller version that it's again free of cost. You can download it. Maybe they will ask you your email ID, name, etc. But then if you really want to test it, scalable system, then it's a commercialized version. You have to pay for the license. And this allow you to have, they have 250,000 buses. So it's a really large system that you can scale and then test it. So you can do steady state and transient stability framework. It's evaluate power flow analysis. They have some functionality called SimAuto. SimAuto allow you to connect. So for example, if you have an interface, so what generally we can also do is I can create a tool in Python, communication interface or whatever, and I can connect Python to this software through interface called SimAuto. Right? If I'm making changes on the interface, I'll show you how it works in the other. I can pass that behavior in the simulation and then run it. So I can attack on my Python module, and then passing that behavior, those change values to the power word, and then simulate it. So again, it's supporting Modbus protocol. And what we look into is the behavior-based monitoring and power system monitoring. Behavior-based means how user interacting, what devices, communication, changes, and so on. The protocol level understanding. And then power system monitoring in a way, when you run this, how the system behaves, what it looks like, whether lines are overloaded, if you have what action you need to take, and so on. This is all about security analytics. Modbus, maybe you can skip all that part, but possibly what you need to understand Modbus supporting level 2 with serial lines, slave bus, master slave, or it can support TCP as well. So depending on the application that you are working, you can use Modbus protocol for layer 2 communication. There you don't need internet. Device can talk to another device directly. If you are fetching data, sending it, connecting it internet, you need Modbus TCP. Yeah? So there are variations of protocol. Oops. Again, Modbus, whether you talk about Modbus, DNP3, all these protocols are proprietary protocols. They've been designed to do certain tasks. They were not designed for cybersecurity anyway. But now we are using them and identifying, oh, they all are insecure. There are a lot of vulnerabilities. And how you derive this? Have you accessed CBE, by the way, on web? So if you Google it, CBE, you get to a website. It's a CBE data set. And there, if you type Modbus vulnerability, you got a list of that. So these were the possible vulnerability have been identified on Modbus. So you got to know what are the issues. As an attacker, you need to exploit one of those, in order to get into the system. And they also give you an update. For example, this one says this vulnerability has been modified since it was last analyzed by NVD. It is awaiting a reanalysis which may result in further change to information provided. So someone has reported. People around our researcher, they can report that there's a vulnerability they find. They kind of give some proof. They evaluate. If they find it's true, they'll publish it, so that anyone get a sense, get to know that this is the vulnerability. If you're using Modbus, pay attention to it. Right? But then people also look around, are there any patches? If there are patches, they will update it, saying there's no vulnerability, this has been fixed. Yeah? By looking at this database, you get a sense. What are the current vulnerability on this particular server, on this protocol, and so on. So it's a really nice database for help us. We also did some experiments. So one of the experiments what we did is disruption of communication loop as a result of Modbus field flooding attack. So we perform a DOS attack. And the whole idea is HMI is fetching data from PLC in a loop. So if you see this, they're looking for temperature and humidity values. And we said here that every 7 milliseconds, so what is happening? HMI sends a request, waiting for a response, saying send me data. Waiting for a response, and get a response, get the data, and then you acknowledge it, saying I got my data, I got data. Yeah, so every few minutes, doing the same thing. So in this particular case, it was 7 milliseconds to complete the loop in terms of sending request, getting your data, acknowledging it, and then they are doing in every 100 milliseconds, right? So you run a loop for 7 milliseconds, wait for 100 milliseconds, then again run 7 milliseconds, then wait, and so. And then we tried to fabricate an attack. We crafted an attack that can be injected in that 100 millisecond gap. Yeah, so we created a fabricated packet, put the sequence number, acknowledgement number from the previous packet, and injected just after that. And as a result, we were able to create a DOS temporarily for some time. Yeah, so you can disable that device temporarily. Was a small attack that we did. So in a way we change the protocol data unit and so on. So I'm not going to detail, but just give you a reflection that it's as easy, as simple. And most of these information available online. What are the vulnerability in Modbus? The number of documents available, how does Modbus protocol works. Yeah, and if you understand what are the issues, how can you tweak this, you can perform large number of attacks on this. So if you see this, we have injected number of packets here, the kind of orange line you see, and the system doesn't understand it. For them, it seems to be an error. There's some kind of error that is temporarily blocking it. However, it's in fact an attack that blocking this device to respond. So it was a kind of few seconds attack. I might change it to a more kind of catastrophic attack. I can compromise multiple devices, multiple PLCs in a similar way, yeah, that are part of real-time systems. So this is one of the simulations. This is the video, just watch it. I don't know if you can see things, but but then we just want to run that software, the simulation environment. So we are initializing number of nodes as a communication nodes. We're describing how many devices we have, what is the power system model we are using. So power system has different model depending on how large system you want to test it. So they have a small test sort of scale system, and then larger, we call it IEEE bus systems. So that's how it looks like. Once you are able to run it, you are creating number of nodes, connecting system all together, and then you can inject data at any point in communication network or so, and then you run the whole loop and test it. So this is what we kind of analyze with this experiment as well, where you see it says unauthorized write request to a PLC, classification potentially bad traffic. So we are mounting an attack and seeing whether it's working or not. So in some sense, in some places it gives you warning, but others it doesn't. We also run say capture the value under the normal scenario. So under the normal scenario, this coil value should be 1. But then when you are saying Modbus query exceeding the expected threshold, and it becomes 0. So that's how you can create a fabricate packet and inject it. Yeah, we are also looking at some matters, for example, sensors, their source IP, port numbers, destination, and so on, what protocol they are supporting. So you need this kind of all information to understand. If you got any suspicions, you need to look into and then build your understanding whether this is actually a malicious packet, malicious command, or it's a routine command. Sometimes it can help you if someone has injected and it's kind of, we can have indicator mostly from IT side. IDs can flag it saying this is suspicious, look for source IP, blah, blah. But sometimes it's, as I said, it's a fake, but the legitimate command, someone has sent it. But from the legitimate device, it becomes impossible for you to know. Then only what we can do is run it. You run it and test it and understand what's happening. Yeah. Okay, I'll pick one more topic before we end for today. Public subscriber smart grid model. So again, it's a too complex model. There's so many devices there. And what is public subscriber? Have you heard this? Public subscriber model? Okay, it's very similar to the way you have feeds, right? So it says, so people always say, oh, press the bell icon, and whenever I publish a video, you get a notification, things like that, kind of thing. So you got publishers who publish on different topics. You got subscriber who subscribe to the topic. Whenever there's a content by publisher, subscriber gets a notification and then can access your data. Yeah, so that is kind of model that we follow. So let's say one device sending data that should be sent to 100 devices. So it should not be like you are sending 100 commands to send that data to every other device. Rather, I will follow this model, and all those 100 devices will act as a subscriber to this device. Whenever this device publishes anything, send anything, it will automatically be sent to all those devices. Yeah. So public subscriber model, they follow unicast, multicast, broadcast communication. We know what is that. Yeah. In most of the time, we do use multicast message. As I said, public subscriber model. We need to, whenever there's a publisher publishing anything, there are many subscribers. Not all, so that's why we are not saying broadcast. Many subscribers, that's why we're calling it multicast. Yeah. And this can be done parallelly, so you need not to wait sending one and then sending other. You can do this at the same time. It's allow you faster response, reduce delivery latency, and so on. So we call it a poll. Whenever you need data, you send a poll request. Yeah? And then you got a response in this substation set terms. For substation, we have some IEEE standards for power substation called IEC standard, IEC 61850. Maybe for us it's weird to remember, but if you ask any person who work on power system, mostly they know this. It's similar to if somebody asks you, do you know OSI model? You say, yeah, I know it. Yeah? It's very similar to them. Anybody who's working around power system, they know this. What is this standard? It talk about how you manage power system at substation. Yeah? Security feature communication protocol used in substation automation are not included because security was not their priority. They haven't designed their protocols, methods for security purpose. So that's why there are two issues. One, high speed performance requirement. And for some processors, they really need data faster. Messages need to be sent in very fast. So it's hard to put in security. Now we have IoT, lightweight cryptography, XYZ. Well, like 10 years back, 20 years back, there was nothing like that even. Yeah, we were relying on either RSA or we were still saying DES, those kind of things. And second is limited computational resource of the deployed IEDs. If you are using IEDs, RTO, those devices, they have their own limited capability in terms of processing power, in terms of storage, and so on. So they can't handle heavy computations. Yeah, you can't deploy their RSA. Say, oh, pick the large primes and do this and do that. They don't have that capability to do that. So in most of the places, we don't have any security control in place. Or if there's a weak or default security where people are just XORing or kind of. Now, if I look at this, so this is the typical scenario. Substation, you got different IEDs. The merging unit, you got different IEDs connecting to HMI, router switches, this is SCADA system, control center, and so on. Now, many of these protocols, devices actually, many of these devices operate with protocols at layer 2. In order to operate them, in order to communicate them, they don't need internet because they are layer 2 devices. They can exchange data. Now, what are the most issues? Not just power system, but let's say talk about IT systems. What are the protocol at layer 2? Have you heard ARP? So there's always saying ARP spoofing, poisoning, RARP. What are those? Most of these protocols don't have security at all. And the way they work, they're just saying, so for example, ARP is used to derive IP to physical MAC address. If you know IP address of a machine, you wanted to know the MAC address of this machine, you send an ARP packet and then get the IP address. So these are, you broadcasters saying, I have this IP address, who hold this IP address, send me your physical address. So you are broadcasting to all the machines. And whoever hold this, they send there, say I got this machine, this IP, and this here is my MAC address. Now in this process, there's no authentication, nothing. As an attacker, if I can respond faster than the actual device, that server will consider my device as the legitimate device, and it will discard the next response that they receive. So it considers the fastest response and discard everything else, because there's no authentication there. Similarly, we have similar issues here as well. They work on similar kind of pattern. We don't have capacity to have authentication in place, otherwise they'll be delayed. Messages will be delayed, we will not be reaching in time, and so on. So generally, a substation, we have three main protocols. One is called Goose, it's a generic object-oriented substation event. Second is called sampled measured value, called SMV. And third is called MMS, manufacturing message specification. So MMS follow client-server communication protocol. Now we know what is client-server. You have a client, you have a server that's running. There could be multiple clients that can connect to the server. and exchange data. Now, GOOS and SMB protocol follow publish subscriber model. As I said, there could be multiple topic that they can subscribe to, different type of data, for example. The device act as a publisher. For example, RTU, they're sensing data, and then whoever needs that data can send. So whoever needs, they need to subscribe what kind of data you need. So you're a subscriber of that type of data. We call it topic in a way. And there could be multiple subscriber, there are multiple publishers, right? Who are collecting different devices, collecting data, and then sending to whoever needs it. So they follow publish subscriber model. Now we say the IEC 61850 recommends some specific security solutions for multicast messages. Should use digital signatures with RSA algorithm to verify message integrity and authentication. I think we haven't covered this stuff, but just touch it. What is a digital signature? And why do we use it? Yeah. Huh? No, it is more secure. What property we can verify in a way? In what situation you will use digital signatures? Sorry? Okay, what else? Mm-hmm. Okay, so there are some basic properties in digital system in terms of cyber security or in general security. So we know CIA, confidentiality, integrity, availability. For confidentiality, we go for encryption. Integrity, we go for hashing or MAC. For availability, generally we look for some kind of logic put in place. There should not be DOS attack, data should be available, so you replicate data, whatever. There are two more things. One, authentication. You wanted to know in a way, or you wanted to verify the users who are accessing system are the legitimate users. That's why we have authentication in place. And the last is, as I said, and we discussed it, repudiation. If you're sending something to someone, that person should not be denying after receiving it. Or you cannot deny that you haven't sent it. Right? So in the digital world, this should be extremely important. Like you see in WhatsApp, you send a message and you can delete it. But when you delete it, that still leave a footprint saying you created something, but now you have deleted. Maybe your recipient cannot see, your operator still see. Yeah? So we need, in a digital world, we need some proof that can allow us to say the user have seen this, somebody has created this, you can verify who has created this. Otherwise, there will be fake content, it's become much harder, impossible to detect it. So what we do generally, we have a message, we're passing to a hash function. Now we were calling it a hash code. Hash code, message digest, same thing, whatever you call it. Earlier we used to call it message digest because we were having MD5 based algorithms. So we call it message digest. Now we call it secure hash function, we call it hash code. Same thing. So you pass message to hash function, get the code, you encrypt this code. Now when you are encrypting, we are talking about public key cryptography. As we said, we got two keys, one public key, one is private key. Whenever you are encrypting at this point, what we are saying, you are signing it. If you are signing it, you are using your private key, which is known to you. That becomes digital signature. What is signature? Signing the hash code of your message. As simple as that. You're signing a hash code with your private key. That becomes your signature. So you send message along with the signature. Now when people receive it, they want to verify what is the source of this message? Who is the person who has created this? If it is coming from me, for example, you know my public key. Public keys are open to anyone. You can easily extract. Sometimes they are at some repositories and so on. So the recipient receives these two things, message and signature. What he gonna do from message? He knows this hash code. He'll pass it, get the hash code here, decrypt this signature. Since the message was encrypted using the private key, it can only be decrypted using the public key, or the other way. Yeah, if you're performing an operation with public key, you can reverse it with the private key. If you're doing this with private key, you can do this with public key, right? We'll see that what. So since it was encrypted using the private key, that can only be decrypted using the public key of that person. And public keys are known to everyone, so anyone can decrypt and get the hash code of message digest. You got message, you know the hash function, you got the code, and then you compare. Now, what properties we are achieving here? Why we are doing this logic? What's happening here? One, if this message was created by you, if I'm able to decrypt it with your public key, that signifies this message was created your private key, which is known to you only. So you are the person who has created this. So it verifies the source of this message. Second, it also helps you to detect integrity of the message. You can verify whether the message has been tampered in between or not. If it has been tampered, these will not match. If they are matching, that means message that was sent has correctly been received. Right? So that's the reason we use digital signatures to maintain these properties. What are the signing algorithms? What are the algorithms through that you can create digital signatures? Have you studied any of those? So there's one algorithm called DSS, Digital Signature Standard. Yeah, there are a number of algorithms, but the very interesting algorithm is RSA. Now, in the previous lecture, we have seen we were using RSA for encryption. Now we are talking about encryption for signature, right? So what we are saying, similar thing. You got a message passed to a hash function, sign it with your private key, send both things over the network. Your recipient will get these two things. It will verify signature, applying public key of the sender, get the hash code. You have a message passed to a hash function, and then compare it. What makes RSA special? So it says there are two reasons why a message is hashed before signed using RSA. So what we are doing, we are hashing a message and then signing it. Why? Why can't we just sign it? What's the need of having this hash code? Why can't we just encrypt, apply signature key to the message and then send it? Why we are computing hashing over it, and then why we are signing the hash code, not the message? Because we wanted to make sure, first of all, the integrity of the message. Message has not been tampered. That's why we wanted to know the code, signing the code so that people cannot change the code. If you change the message, this will be false. Second property of hash function is for any value of your input, there is always a fixed outcome. Right? Irrespective of how long your message is, your outcome is always fixed, depending on which function you are using. If you are using SHA-1, it's a 160 bits, and so on and so forth. Yeah. So it kind of reduced the signature size. You need to sign lesser number of bits. That's why we are not signing the message. If message is your 1000 bits, your signature will still be 160. Yeah? So those are the reasons why we sign the hash, not the message. Now the question is, why RSA is special? Why we are talking about that RSA can also encrypt, but at the same time they can also be used for signatures. And RSA is the only algorithm you can do these things. There are encryption algorithms you can use for encryption, but you cannot use for signatures. There are signature algorithms. You can create signature, you can't encrypt using them. But the RSA, you can do both things. Why? And that's why RSA is very, very popular. It's widely used. It was considered one of the greatest innovations in computer security when people have invented this algorithm. Why? So let's say you cannot obtain digital signature scheme by swapping the role of private and public keys of any public key cipher system. Then it also says you cannot obtain a public key cipher system by swapping the role of signature and verification keys of a digital signature scheme. And it is the same algorithm that you can use for encryption, you can use for signatures, right? So what are those properties that makes it unique? So that was a task is to identify special property or RSA that allows it to be used as both encryption and a signature algorithm. In real application, you should avoid using same RSA key pair for both encryption and digital signatures. So if you need to create signature, what is the principle? You need to sign message using the private key. Yeah? And you send it over the network. Whoever holds your public key can verify your signature. Now when we talk about the other way, encryption, why do we do encryption? Because we want to send confidential information. When you are doing encryption using public key system, you are using your public key of recipient. If I need to send a message, confidential message to him, I will use his public key, which is known to everyone, to encrypt my message. Since the message was encrypted using public key, it can only be decrypted using the private key of this person, who is known to the person only. So if I can send any confidential message, that person can only decrypt it. Yeah? It will go over the network, but that's in encrypted form. Only the person who holds the private key can decrypt it. Right? So in RSA, you have one pair, one for private key, one for public key. If you are encrypting a message, again, when I say signing, we are ultimately encrypting it in RSA because the same algorithm. It's just the change is which key you are using to encrypt it. If you are using your private key to encrypt it, this will act as a signature. Yeah? Anyone who holds your public key, everybody knows, can decrypt and verify your signature. So that means in this message, there's no confidential information. Rather, I'm sending something so that people can trust this message came from me. You got a notice or letter from director office. Where director signed this, you believe that this is coming from director and these are the instructions. So you see the signature, you verify signature, or this looks from director office because it's on letterhead or whatever. In a similar way, you verify the signatures, and based on that say, oh, this person has sent this. If I want to send anything, I will create signature of it. I'll use my private key to sign it. Anyone who holds my public key can decrypt it and verify signature. So there's no confidential information, rather than information for everybody. The other way, if I need to send anything confidential, I will use the other way. I will use the public key of that person, encrypt it, send it. That person will apply its private key, decrypt it, and get the message. Yeah? Now, practically, we say whenever you are doing encryption or signatures, every time make sure you have a different pair. Don't use the same pair again and again. Otherwise, people can connect that key pair and then can crack it. It's very similar exercise, the one that we did yesterday, where you got public key, and even if you have multiple public keys, and if you're not really generating the way they should be, people can crack it. Now, it is also said the RSA algorithm that we generally study is not secure in a way. Whenever you are using RSA, make sure you are using padding. So whatever your message is, you always add some redundant and always use some padding, some bits out of it. The reason is, in worst case, even if someone can capture it, they can still recover the original message unless they know what padding you have used. Yeah? The person who is having this part will not be able to recover this correctly unless they have understanding that what is the size of padding and so on that you used. And using padding makes your message a little bit more different. If you're encrypting the same message again and again with different padding, your output will be different. So we talk about ECB mode, where you see if you're encrypting the same message again and again, you got the similar patterns. That's one of the reasons you shuffle your input, add some padding every time. Okay, we talked about this bit. So I will not go in much detail, but just give you overview. So we said why we use this. Have you studied this, Diffie-Hellman? Yes. Okay, so what is Diffie-Hellman key exchange? So these are two people, Whitfield Diffie and Martin Hellman. They again published a paper 1976, New Direction in Cryptography, where they come up with this algorithm. Now, one of the challenge at this point of time, before RSA was invented, people were mostly working on symmetric key cryptography. Yeah? And one of the restrictions or limitation of symmetric cryptography is you need to send the same key to the recipient. Yeah? That's the same key that you use for encryption and decryption. Now, they come up with an algorithm saying you don't really need two trouble. We have an algorithm that can help users to generate the same key at both ends without sending the actual key over the network. Because at that point of time, sending anything over the network was a big deal. There was no TLS, no transport link, no SSL, nothing. You are purely relying on encryption. You can send the encrypted packet, but how are you going to send key? There's no email, there's no text. Yeah, they're all 1980s, GSM came 1984, 3, and so on. So there was no cellular phone at this point of time. How are you going to do that? So that's where they come up saying we have an algorithm that can help you. Now, we will look very sort of quickly. The couple of parameters. One is the protocol uses multiplicative group of integers, modulo n. What does it mean? There's a group of integer numbers, 1 to infinite. Yeah? I might have an integer of, let's say, 100 numbers. Multiplicative group. What is that property? Which says if I say multiplicative group of integer modulo n. First of all, I have a group of integers. Multiplicative group means if I pick any two numbers of this group, multiply them, perform a mod over it, outcome should always be one of those numbers. Yeah? You might have additive group of integers. If I'm performing addition of any two numbers, mod n, result should be one of those numbers. So as simple as that. So that's what it says. So they created a multiplicative group of integer modulo n, where n is a prime number. N must be a prime number. G should be primitive root of modulo n. So let's say if somebody gave you n, you already know n, you already know G. G is known to everybody who is part of the group, all the users. So it's between two users, Alice and Bob, and they need to generate the key. So what Alice does, Alice randomly select a large number, x. You randomly generate a number, x, need not to be prime number, and perform G to the power x mod n. Considering you know G, you know n. G is the size, n is the size of group, G is some parameter that every user in the group knows, right? Now you can generate a random number x, you perform G to the power x, and take a mod n. Similarly, other user Bob, generate another random number, perform G to the power by mod n. Yeah. Now these are not the actual key. I'm calling it capital B. Let's say this is capital A. They will exchange these numbers. So Alice will send B over the network to Alice. Alice will send capital A to Bob. Now whatever Alice receives, B, capital B, it will perform to the power x, this number that they randomly generated, mod n. Similarly, Bob receives capital A to the y, this number that Bob generated, mod n. And once you look at this, what is B? G to the power y to the power x. Similarly, the other way, what is A, which is G to the power x to the y, which is G to the power xy, ideally. So G to the power xy means both parties having the same number. And that's how they can generate symmetric key at both ends without sending it. Simplistic way, this is n and g, common parameters. Alice can generate a random number, orange color. Bob generate random number, blue, whatever. They exchange and mix it, right? So they mix yellow, so they mix this, which is A and B, capital A and B, and they exchange it. And now you selected your orange, so you mix orange with this color. You go with this blue, you mix with this one, and you see the same colors. So it's a simplistic way to understand. This is how you can generate the same number, same color, without sending that color or number over the network. Yeah, and it's just kind of mathematical representation of this with some examples how it look like. Now I'll talk one thing only before we go. Yeah, just last slide. What is the issue here? Right. What is the issue here? The issue is there is no authentication. Anyone can send that number and get the same key at both ends. As an attacker, I can send you something pretending somebody else because there's no authentication, and end up with having some symmetric key with that, So you can break this. So for example, in this case, Alice and Bob. Now Alice performs G to the power x, need to send it to the Bob. So Alice send it. However, there is a man in the middle attack. There's an attacker that captures this, create its own number, G to the power z, pick a random number z and perform G to the z. Rather than sending G to the power x, you send this. Right? Similarly, Bob compute G to the power y, sending it to the Alice, but then there's somebody in between, doesn't send this to Bob. So what will happen? They will end up with having a key Z to the power x z. They were having a key called Z to the power zy. So there are two connections, one between this and this, one between this and this. But Alice and Bob has no idea. There's someone in between that has two connections. Whatever you will send with this key, this person can decrypt because there's no authentication in that. So definitely we need to solve authentication problem, but otherwise, this is excellent way of generating the same key. So we'll stop here, and we'll come back at 2:30 for the lab. Thank you.